So we're just doing this as a warm-up. Assign formal charges too. It's always a good practice. Oh, okay. So I'll go ahead and send the attendance around. Just make sure it gets like all the way back one side and back the other, so everyone gets a chance. Did you guys know it's supposed to be like 50 something, 55 or something this afternoon? Now it says there's supposed to be rain. Oh, maybe that's not till later. Anyway, go outside. All right, so I've drawn in red the electrons that are added on, because remember it's a -3, so we need to add some electrons on there. I added them to the oxygen because the oxygen is the more electronegative thing. So there's kind of two approaches that if you're drawing this, you could have taken. So the first would be to not worry about the fact that that phosphorus pair is a pair and just split it up. So if I did that, I would form single bond, single bond, single bond, and then a double bond over here. Okay? This is preferable to this other one over here. So the other way that you could have approached this is by moving an electron in order to get the bonding to look right. Now, just real quick, we've done this before. I'm trying to, let's see where it was. CO is what I'm looking for. There we go. That was not very detailed notes though. All right, whatever, I'll throw it in there. So when we do CO, we start with 4 on the carbon and 6 on the oxygen. So carbon looks like it wants 4 bonds, oxygen looks like it wants 2. Obviously that's not gonna work out. We need them to want the same. And the other thing is we know that carbon and oxygen firmly obey the octet. So the only option is to move an electron over from oxygen to carbon. So then we form triple bond and get this guy. That process of moving the electron is what causes carbon to have the -1 formal charge. So as a quick review for that, carbon started with 4, And now it has 1, 2, 3, 4, 5. So it is -1. I know that because if I'm given the structure, I can calculate it like this, but I know that that's what I did when I drew the structure as well. I moved an electron to carbon. So that gives it a -1 charge, and it gives the oxygen a +1 charge. Again, 1, 2, 3 for this oxygen, 4, 5. So 6 minus 5, +1. Okay, so I could do the same thing for the phosphate. I could move that electron over to make the bonding look a little bit more comfortable, not have to break up that pair, right? So if I do that, and I move one of these electrons over here, that actually looks really nice, right? Like I can go ahead and bond single bonds to all the oxygens. Everybody's octet is satisfied. Phosphorus isn't overfilled. But that process of moving an electron gave a formal charge to the phosphorus and the oxygen. Now, again, you can go through and calculate these to like verify that. But when I did the structure, if I had to move an electron, I know that I just messed up my formal charge. Here, I didn't move any electrons. Oh, wait, that's not, it's true that I didn't move any. Anytime you add an electron, that's also going to give it a formal charge, right? I added those red electrons, which gives a charge to all of those oxygens. Same thing on this side. That's expected, because anytime we have an ion, all of the formal charges have to add up to that ion. So PO4 3-, the formal charges have to add up to 3-. So that comes on these 3 oxygens. The question is, are the other 2 atoms going to have a formal charge, or are they going to be 0? So this is definitely our preferred structure because I'm getting a lot closer to 0 with those. I've got 2 that are 0 and 3 that are -1 versus 4 that are -1 and 1 that's +1, right? It's always preferable to not have to shift those electrons around. Sometimes it's unavoidable. But like a sample test question would be, I give you both of these structures. I was trying to erase the formal charges and also draw them a little tidier. So let's go like this and then get rid of these guys. Okay, so let's say I give you both structures and I say, so you didn't draw the structure, I just gave it to you. Oh, and technically, to make these look all nice and correct and pretty, I need to put the charge on there. And I say, tell me which structure is best, decide which structure is best, the most accurate Lewis structure, by assigning the formal charge and then, using that to tell me which structure is best. So that one with the double bond ends up with zeros on 2 of the atoms versus all of the atoms having a formal charge over here. So that is our preferred structure. It doesn't matter that it broke the octet, right? Phosphorus is n equals 3. Anything n equals 3 or further has those d orbitals available, and there's no reason why it can't use them. Another way of saying that is like formal charge always trumps octet obeying the octet. Obedience. Octet obedience. It's a new one. Okay, there's one more topic we need to cover. Maybe I'll use phosphate as an example. Erase this structure that's not very good. Okay, remember, oh gosh, I don't want to have to draw 4 resonance structures. Okay, so technically there are 4 resonance structures for this. So if I were to draw the Lewis structure for this atom, I'm going to be lazy and not draw all the lone pairs for you guys. I don't even have room for all the structures. Okay. All four of those together, drawing them complete, putting the brackets, putting the lone pairs on there, putting the little double-headed arrows between, that would be the best representation of the Lewis structure, because it is telling us that the real structure is an average of all four of those structures. Did anybody not get this? Okay. All right, so another way of saying that is that each of those oxygens looks like it has 1 1/4 bonds. When we talk about the number of bonds, we say bond order. So like a single bond would just be a bond order of 1, double bond would be a bond order of 2. It's most useful when we're talking about things that aren't a whole number. So the bond order here would be 1 1/4, because that additional bond is actually spread over all four regions. So it's like 1/4 of it is one place, 1/4 of it is another, 1/4 is another, and 1/4 is another. It should be a little bit irksome, but remember, electrons aren't particles. They behave a lot like waves. They can spread themselves out. Okay, the reason why we know that that's true, why we know that resonance structures are a thing and that it's an average of all of them, is because we can look at the strength of a PO bond in phosphate. All of you biologists, this is like ATP, right? Adenosine triphosphate. These are the phosphate groups that are stuck in there. So when we look at the strength of each of those bonds, they are all the same strength. When we look at the length of those bonds, they are all the same length. And they are all stronger than a single bond, but only by a little bit. They are still significantly weaker than a double bond. So their strength is closer to the single bond side, but stronger than a single bond. Now, we haven't talked yet about the fact that as the number of bonds increases, its strength increases. So that's kind of the last topic we need to hit today. So first, to define bond energy, because if you had me last semester, we skipped over chapter 4, or 7. So we haven't talked about energy a whole lot, including bond energy. We will do chapter 7. I think it's the next one. I think it's next unit. I think it's the first chapter we're going to do after the exam. Okay, so bond energy corresponds directly to how strong a bond is. Because bond energy is just the energy it takes to break a bond apart. So if it takes more energy, that's just another way of saying that the bond is stronger. It's more likely to stay together. Every time you break a bond, it takes energy. Okay? Every time you form a bond, it releases energy. So when we look at bond energies, so here's the hydrogen-hydrogen bond energy, that's telling us the energy. Now, this is for, 6.022 times 10 to the 23rd hydrogen-hydrogen bonds, H2 molecules. It would take 436 kilojoules to break apart those bonds. If you had the hydrogens separated and they came together, it would just release that amount of energy. Don't worry about this negative thing. We're going to talk about that in chapter 7. Okay, so I'm just going to skip down. Let's look at this table first. So if we look at a fluorine bond, single bond, hydrogen bond, carbon bond, a single oxygen bond, that gives us an idea of how strong those bonds are. So it's kind of interesting, actually, that the hydrogen bond is the strongest of those. In some respects, it's interesting. In others, it's H2, It's pretty stable. We know that it's diatomic. We know that it sticks together pretty well. So this tells us an idea of the fact that like the fluorine bond is relatively weak. It's going to be pretty easy to break that apart. Okay. All right, this is getting into what we were talking about earlier, that if we increase the number of bonds between given atoms, it's going to increase their strength. That shouldn't be that surprising, right? It doesn't triple it when we go from a single to a triple, but it's kind of close. So every time, this shouldn't be that surprising, because every time you add an attraction, you're adding another attraction between the nuclei and the electrons. That attraction, you're going to have to break it apart if you're going to break the bond. So this only works if you're comparing the two same atoms, not necessarily carbon and carbon. You can do this with carbon and nitrogen. But you can't like compare a carbon-carbon single bond to a fluorine-fluorine single or double bond or something. That doesn't work because fluorine doesn't form double bonds. An oxygen-oxygen double bond, okay? You have to compare the same two set of atoms. All right, the last thing I want to do is compare these bond strengths to bond length. So I'm going to try hard to remember these numbers. 837 and 847, okay. Or 347, and then 611 in the middle. I'm going to go down to this chart down here. That one was this 37, is that right? I don't remember if I got the 37 and the 47 in the right spot. Let's see. No. Oh, yes, okay. All right. So what we would expect, stronger bond, triple bond. Now we want to look at their lengths. So just one slide up. So these are the bond length, meaning how close are the atoms together. Carbon single bond, 154. Carbon-carbon double bond, 134. And triple, 120. I even have the picture kind of showing them closer and closer together. So as you make more and more attractive forces, remember, things that are attracted want to be close to each other, and so they pull in tighter and tighter. That's also what makes them stronger and harder to break apart. It's just like if we had the nucleus and an electron, the closer they are to each other, the stronger together they're held. This is why the core electrons aren't the ones involved in bonding, okay? So if we add additional attractive forces, which is what a bond is, they get pulled in closer and they have a higher energy to break them apart. So bond order, 1, 2, and 3. This guy is going to be the strongest and the shortest. So when we looked at that PO bond in phosphate, it was somewhere in between a single and a double bond, both in strength and in length. Go back up to that real quick. Yeah. So all 4 of the bonds are equivalent. That's what the resonance structures tell us. And each of the bonds is going to be slightly shorter than a single bond and slightly stronger than a single bond. So that's how we're kind of like verifying that this Lewis structure is accurate. In fact, that one that I erased where they were all single bonds, that is a good way to verify too that that one was not accurate, because we know what a PO bond should look like, a single bond, and the PO bond in phosphate does not look like that. It does not look like a single bond. It looks like 1 1/4 bonds. So it's a good validation for this being the most accurate Lewis structure. Of all the types of chemistry, I was the worst at organic chemistry, so I've never taught it. There's some times where this kind of stuff makes me feel like I kind of would like to, though, because this stuff is so crucial. So like OChem is the building blocks of biochemistry, which is the building blocks of biology. I'm sure the biologists would love me saying that. But it's true. Like over the last 30 years, we have understood more and more of the chemistry of biology. And a lot of this goes into that. Understanding that that electron group gets kind of spread out helps us understand why phosphate is so stable. If you can't spread that out, it makes that double bond more reactive, but we don't see that happening. Okay, that's the end of chapter 10. There was an issue with Pearson last night. So if you're a procrastinator and you waited until like 8:30 to do it, there was like a lag. It wasn't even a lag, like I couldn't get the assignment to load. So I extended that in case you need it to tonight. If you did a first pass, like you only had time for a first run through and you got one wrong, just go back and redo it tonight and earn those points back. The homework for chapter 10 is due tomorrow night, and you definitely have everything you need for that now. And then the practice exam for chapter 10 is open. So it's not due till the night before the exam. What I would recommend, you have 2 attempts per question. I hope it's 2 and not 3. But I think you have 2 attempts per question. Do 1 attempt maybe by the end of this weekend to get a feel for like, am I good with chapter 10? Do I need to study more? And then if you need to re-answer some of the questions, do that as you're studying for the exam, end of next week. So that's what I would recommend to do with that. Okay, chapter 11. So it's kind of hard to break up these topics. So I have it listed for 2 days. I'm only going to go as far as my other class went, though, so we will probably end early today because I like keeping you guys as much as possible on the same topics. Okay? So the first step in chapter 11 is drawing an accurate Lewis structure. So we are still going to get lots of practice with drawing good Lewis structures. So that's kind of reassuring. The rest of the stuff is translating those 2-dimensional pictures that we have with a Lewis structure into understanding what they look like in 3 dimensions. Because molecules exist in 3 dimensions, they react in 3 dimensions, so we need to think about them in those terms. Rumor has it that the lab this week is about this stuff, so that should be helpful. So what we're going to do is use this simulation. This is one of those, like when your dad says, I had to walk in the snow to school, uphill both ways. When I was learning this stuff, we did not have simulations, as bizarre as that seems. We had the internet, I promise, but we did not have some nice 3-dimensional representation of things. And we had to use model sets. And like in organic chemistry, you use them so much that we were allowed to bring them to our exams. And so you'd hear this like pop, 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 as people are like making their little molecules so they can visualize them, so they can know how they're going to react. So just a, reminder that it actually really is important, especially as you move on, to be able to visualize these. But thankfully, you can visualize them 3-dimensionally with a computer model. All right, so you're going to want to use this. I would say certainly for any practice you're doing this week through the weekend, use this to visualize things. Once you get to like the end, like Monday, the homework, you probably should stop relying so much on visualizing it with this because you're not going to have this on the exam, and start trying to picture it in your head. So we're going to go through the examples for 2 groups and 3 groups surrounding the central atom. So when we talk about this in the groups, we're always talking about whatever's in the middle and what's surrounding it, because that kind of defines the geometry at that given point. So we're going to talk about 2 groups and 3 groups. We're going to address what happens when there's a lone pair in there, and then we'll finish 4, 5, and 6 on Wednesday. Okay? So let me go back to the notes. I'm going to go back and forth a lot. So we are going to write down examples of molecules that these 2 we've looked at already. That have 2 groups surrounding the central atom. So there's one, and CO2, there's another one. Okay, so we're starting with a good, accurate Lewis structure. What do I mean by groups? A double bond and a single bond, they fill the same physical space. So that would count as one group. So a single bond, a double bond, a triple bond, those all take up a certain amount of space, and it's equivalent, whether it's a double or a triple. And so we just count that as one thing, one group. Sometimes you'll hear a region surrounding the central atom. So 1 region, 2 region, 1 region, 2 region. And what we need to think about is how those regions separate themselves. Bonds are electrons, okay? They're negatively charged. They do not want to be next to each other. So they are going to separate themselves as much as possible so that they can be as far apart from each other as possible. It's pretty obvious that when there's 2 groups, the best way for them to separate themselves is straight across from each other, okay? So we'll look at this in the thing. It's not nearly as interesting as when there's 3, though. They're straight across from each other. Okay, you can click on the thing that says show bond angles. That shouldn't be surprising. 180 degrees, that's, oh, will you turn off this light now? I said to leave it on, but now I'm understanding why it was off. No, sorry, off. That one off and this one off. I think I said on. That's better. It's not perfect, but it's better. So 180 degrees apart from each other. We're going to give all of these names. And there's 2 different types of names that we're going to give them. The first one is how the electrons are arranged. That could be electrons in a bond, or it could be lone pairs of electrons. When we're talking about 2 groups, they're always bonds because it just doesn't really make sense to talk about the shape of 2 atoms. Okay? So on the bottom here, you'll see it says electron geometry and molecular geometry. The other terms you'll hear for this are electron pair arrangement, or maybe electron arrangement, or electron geometry like it is on the model. Those all mean the same thing. If it's talking about the electrons, it's talking about the same thing. And what we mean by that is how the electron groups, whether they're bonds or lone pairs, how they orient themselves. So in this case, there aren't any lone pairs on the central atom. We don't care about the lone pairs on the fluorine and the oxygen right now. We're just looking at the atom in the middle. So there are no lone pairs on there. They're just bonds, and they're just straight across from each other. So the way the electrons in the bonds orient themselves is called linear. The other label that we're going to give these is called the molecular, so this is the key word, or molecule geometry, or maybe shape. And this is if you trace the shape that the atoms take on. So in this instance, it's the same thing because all of them have an atom connected to those electron groups. So when we do 3 groups, this will be clear when it's different and when it's not. But for now, both of those groups have an atom attached to it. And so we also call the molecular geometry linear. And that'll be true anytime there's no lone pair on the middle. the name should be the same, okay? Because this is describing how the electrons are arranged, this is describing how the atoms are arranged, but there's no electrons that aren't attached to atoms, so they should match up. They should both be called linear in this instance. And we said already that the angles are 120. Okay, let's do 3 groups now. So one example of this would be BH3, which we did that one previously. Oh, I think we did it. I feel like in the notes it looks like, okay, just kidding. Verify that that's the right Lewis structure, okay? So I want you to draw me a Lewis structure of BH3, and I also want you to draw me one for SO2. SO2 is gonna take you a little bit of time and thought, okay? You might want to consider formal charge. So hopefully you remember from our kind of list of octet rules that bromine is one of those that underfills. And that's why it's okay that we just pair up those individual 3 electrons with the hydrogens. There literally is no other way you could draw that anyway, so. Okay, so if you're questioning at all what you should do with SO2, this is very similar to phosphate. It's similar to sulfate. Your choices are, you can, really you have to move an electron here. Let's talk about why. So let's put a single bond there, a single bond there. Now, I don't have to move an electron, I lied. Okay, I could move an electron. So let's say I don't move electrons because that's really our preference. And I'm just going to split up one of these pairs and make a double bond there and a double bond there. That is our best structure. Also, you probably knew that. Oh no, I guess the other one would have 3 groups as well. I was gonna say you probably knew that because this is our example of 3 groups. But the other option, so this is preferred. We didn't move any electrons. If you check, all of the atoms have a 0 formal charge, which is great. If we wanted to, maybe we were stuck on the idea of the octet, we could have taken one of these electrons and moved it to the oxygen, and ended up with, is that right? Let's see. 6 times 3 is 18, or 9 groups. 1, 2, 3, 4, 5, 6, 7, 8. I don't think you can do this. I think you wouldn't be able to satisfy the octet that way. 2, 3, 4, 5, 6, 7, 8. Oh no, like this. 9. That's an option, but it's a bad option. The only reason people would do this is because they had the octet rule drilled into their head too much. Okay? So, yes, it keeps the octet for sulfur instead of overfilling it, but this one ends up 0, this one ends up -1, and this one ends up +1. Okay? Our preference is always to have everything 0. Don't care that you broke the octet, because it's not a rule, it's not a firm rule for n equals 3 or above. Oh, there's the pair. I was like, where did that other electron go? Okay. All right, 3 groups, one of which all has an atom, one of which has a lone pair. So this is where we're going to start to see some differentiation between how having a lone pair affects the shape. Okay? So, boron, 1, 2, 3 groups. Sulfur, 1, 2, 3 groups. Remember, a double bond just counts as one group, or region, or whatever you want to call it. Okay? So let's go over to our thing. So this one is the model. If you see down here, when when it loads, you can click model or real molecule. So this is one where you can just tack on as many bonds as you want to look like the structure that you drew. Okay? So everybody watch. I'm going to hit bond, and I'm going to throw another bond in there. Okay, 3 things. They all need to repel away from each other as much as possible. So if I have 3 things, they end up in a plane 120 degrees away from each other. That is the biggest separation that they can have. If I try to move one of those atoms, in fact, I think you can do this on here. Yeah, if I try to push an atom down, it just pushes it back to its desired location so that they're as far apart from each other as possible. It's because the bonds are made of electrons, right? So they're repelling each other. So it is a flat surface, a plane, and there are 3 of them, so we call it trigonal planar. Again, because there are no lone pairs on the central atom, the way the electrons are arranged is the same way that the atoms are arranged, because they all have an atom tacked onto those electrons. And so the name of how the electrons are arranged and the name of how the atoms are arranged, those are the same, trigonal planar. The angles are 120, just like if you had a triangle, 360 divided by 120. Okay, so the electron geometry, trigonal planar. The molecular geometry, which again, you want to just trace the atoms. That's also called trigonal planar. And then the angles are 120. All right, next one. We still want 3 groups. So before I even go to the thing, I know that the electron geometry is still called trigonal planar because there's still 3 groups of electrons. So that doesn't change. That's completely just dictated by how many groups are surrounding that central atom. And really, I should predict that the angles are 120 as well. We're going to see that lone pair squishes the angle a little bit. Okay, so I'm gonna delete one of the bonds and add a lone pair instead. Okay, so it still takes that same general shape. If you're just looking at electrons, electrons as a pair, electrons as a bond, it's still 3 in a plane, right? That's why we still call the electron geometry planar. And this is the model, so it's still predicting 120 degrees for the angles. But if we trace the atoms, the outline of the atoms is no longer trigonal planar. There's only, this one shape, this one little pie piece. We call that bent. So that's this one down here. So again, molecular geometry, trace the outline of the atoms. It's like the electron pair hugely influences the shape that the atoms take on. But then we kind of like say, let's pretend they're sort of invisible. They're having an effect, but we don't physically see them because they don't have significant mass. So we're just looking at those things that have significant matter concentrated on them. Okay, if I actually go to the real one and look at SO2, the bond angle is slightly less than 120. So we predicted it at 120, it shrunk slightly. That's because a lone pair, if it is stretched out between two atoms and as a bond, it's long and skinny. If it doesn't have an atom that it's attracted to up here, it kind of bulges out so that those two electrons take up a little bit more space. And so it squashes those angles down. Because remember, it's pushing against repulsion here and here. And so it pushes those a little bit closer. You don't have to know that it's 119. Just know that it gets a little bit smaller. So back to this. The molecular geometry, we call it bent. And the real angle is slightly less than 120 degrees. So Lewis would have drawn the structure. In fact, he would have probably put these lone pairs at perfect corners or edges of the structure. Okay, he would have drawn the structure like this. That is not what the structure looks like, okay? It looks like trigonal planar. It looks like this. That gets even harder when we have 4 groups. It's even harder to describe on a flat paper surface. This is pretty good, okay? And when we can do that, we will start doing that just because it's helpful. For example, like lone pairs have the tendency to react with other things. So knowing that this lone pair is up there and that I could bring in another group to bond with it is really helpful. And seeing how that would look when it bonds is always better to have it look like it's actually going to. Okay? So we'll do 4 bonds on Wednesday, but just as kind of a preview to that, if I add 4 things in, we are no longer talking about a plane. We are very much inhabiting 3 dimensions at that point, so it gets a little bit trickier. Okay? All right, we'll stop there so that we're on the same place as my other classes.